Hi, I am Abdulrahman Kerim, and I will be very happy to present our paper titled Leveraging Synthetic Data to Learn Video Stabilization Under Adverse Conditions. Stabilization plays a central role in improving the quality of videos. Recent video stabilization approaches perform well under standard conditions, but struggle under adverse ones. Moreover, collecting training videos in these adverse conditions is hard, dangerous, and really time-consuming. Usually, feature extraction, description, and matching are involved in this process. In the video stabilization process. Feature extractors like SIFT and the learning-based ones like R2D2 perform well under standard conditions, but they may fail under challenging conditions. By challenging conditions such as foggy, rainy, and snowy weather, as well as nighttime scenes. For instance, raindrops and snowflakes, particles, along with texture-depleted scenes in fog or darkness pose a clear challenge to extract robust features. Failing to estimate the camera trajectory accurately in the motion estimation stage, propagates the error to later steps of the process, decreasing the quality of the stabilized videos. Now, synthetic data have shown a great progress in the field of computer vision, captivating numerous researchers who seek to apply it to diverse computer vision problems. Our proposed method does not require any real data for training and is more robust than state-of-the-art methods across different weather conditions. To the best of our knowledge, this is the pioneering work addressing video stabilization in adverse weather utilizing synthetic videos. Now let us briefly discuss some related works. Traditional feature extraction approaches such as SIFT and OAN with outlier rejection algorithms such as RANSAC and MACSAC do well under standard conditions such as normal weather conditions and sufficient illumination. But also they perform poorly under challenging scenarios such as adverse weather conditions and insufficient lighting. While supervised approaches may be seen as a solution, they usually can't reflect scene parallax and generating suitable training data for them under challenging conditions is so hard. At the same time, unsupervised approaches fail under large baseline alignments, thus they are impractical for video stabilization under sharp camera movements. Now, while there are some works on synthetic data and video stabilization close to ours, however, they present a partial solution to the problem. For instance, Sim2Real VS uses GTA 5 video game to generate the required synthetic data. However, the game was not originally designed for synthetic data generation. Thus, Sim2Real VS is limited to GTA 5 assets, while our simulator allows us to procedurally create new cities for each synthetic video and easily modify or add scene elements, which is not possible with Sim2Real VS relying on GTA 5 game. Additionally, our work does not require user manipulations, and it applied uses basically a relative simple architecture for the video stabilization task. Finally, it doesn't require complex hyperparameters tuning. Our contribution in this work are threefold. One, a novel synthetic aware video stabilization method achieving state-of-the-art results on real videos while trained only on synthetic videos. Two, a synthetic data generator capable of producing specially designed training videos for video stabilization task. Third, a new video stabilization data set, VSAC 105 Real, composed of real videos spanning foggy, rainy, snowy weather and nighttime attributes. Our method is composed of two stages: motion estimation and trajectory smoothing, as you can see in this figure. Our video stabilization method first estimates the translation, rotation, and the scale for each pair of frames of the given shaky video. After computing the camera trajectory and finding the upper and lower bounds, we average them. Then, the Savitsky-Colai filter is applied to smooth the trajectory. Finally, warping and cropping are performed to give us the stabilized version of the video. Our video stabilization is completely trained using synthetic data generated by our simulator. These are some samples from the procedurally generated scenes using our proposed synthetic data generator. We can generate photorealistic scenes under various weather conditions, time of the day, with the ability to randomize scene attributes, such as characters created, building types, and materials, and many others. Another key contribution of our paper is the VSAC 105 Real dataset, which includes more diverse and challenging attributes as compared to other datasets such as DeepStab, StabFR, Selfie Video, and others. The ground truth generation mechanism is a fundamental component of our approach. First, in A number of points are randomly sampled from the screen space, as shown by yellow circles on A. Then, from each of these points, we cast rays to infinity in the 3D scene space, as shown by the dashed yellow lines in B. Following this, we create hypothetical objects at the intersection of these rays with the scene, as shown by the red circles in C. Now, we obtain the affine transformation matrix AI using the coordinates of the hypothetical objects in screen space, Pi and Pi plus 1, since they remain stationary in the scene from frame Vi to frame Vi plus 1. Then we use the generated synthetic sequence with the calculated AI to train our video stabilization approach. For more details, please check our paper. Now, to assess the usability of our approach, we compare our method to different state-of-the-art video stabilization approaches, such as FUSTA, Grandman, StabNet, Different, and Yitito. We use well-known and commonly used metrics in video stabilization literature, such as stability average score, distortion score, cropping ratio, and our proposed success rate metric. As we can see, our method presents a good solution and achieves a better performance compared to other baselines on the VSAC 105 Real dataset. For additional results on Selfie dataset, please refer to our paper and supplementary materials. Then, to validate our design options, we perform a set of ablation study experiments. First, our method uses two fully connected networks to learn shaky camera trajectory. One that estimates the translation, and the other estimates rotation and scale. To see the impact of using single network to learn these four parameters, I mean translation on the horizontal and on the vertical axis, and to learn the rotation and to learn the scale, we report the results in single network variant. Then, to understand the effectiveness of our parameters estimation network, we replace it with SIFT and report the results. As we also use optical flow, we also study the impact of training our method without this modality. Then we assess the impact of training our architecture with excessive synthetic data. Finally, we can see that our complete model gives better results compared to other variants. Thank you very much. And if you would like to access the synthetic dataset, the real dataset, the code, or our simulator, our data generator, then all these are available under the paper's GitHub repository. If you have any questions, and if you would like to contact us for any future collaborations, this is my email.